As you can see from the title of this video, this tutorial is about determining the percent composition of a compound. If we're going to discuss percent composition, we should start about why percent composition of things is important. The main idea behind when percent compositions are used is mostly for identification purposes. If we take an unknown sample and we can determine how much of it is of each particular element, we can match that up with known compounds that have that same percent by mass of elements, and we can have a pretty good idea of what that unknown substance is. A great example would be from the summer. NASA landed a rover on Mars that was taking pictures, and we are not far away from it being having something that can collect samples of substances, right, to test for percent composition, to see what types of elements, right, and what types of compounds could possibly exist on a foreign planet. The main thing that you would think they'd be looking for is water, which means they would have to find something that is the right percent composition, hydrogen to oxygen, so that we would know if it is water, because you might not be able to tell simply by looking at it. Anytime you're doing a percent composition problem, you want to use a fairly simple equation. That equation is this. Percent composition of a compound is equal to the mass of one of the individual elements divided by the mass of the entire compound. Because it's a percent comp, we have to multiply it by 100%, just like you would do to your exam grade, right, to get yourself a percentage. If you get 7 out of 10, it's not 0.7%, it's 70%. So the same idea here. One thing I want you to realize as we go through is that there are two types of percent comp problems. There are theoretical percent comps, and then there are actual or experimental percent comps. So what is the difference between the two? It's pretty straightforward. The theoretical percent composition of a substance is what it should be. What should the percentage of them be? And we solve these problems by using the periodic table and a formula. If it's an actual percent composition, that means we gathered information in the laboratory and obtained actual numbers by putting them onto the balance to get these. That means you do not use the periodic table. Where then do we get numbers from to solve the problem? We either use lab data, or they're simply given to us and we didn't actually have to perform an experiment. It's a hypothetical situation where you're posed with information given. So I'd like to do a problem of each type and then try to tie those ideas together to figure out if we were performing an experiment and we know what the result should be, how we can compare those two numbers as a way of measuring our effectiveness in the lab. So the first question would be on a handout that you could print out, but I have it written up here also. That handout is called percent composition. It says, determine the theoretical percent composition of sulfuric acid. Now this isn't a quiz on compound naming, but sulfuric acid is an ic acid, which means it used to be hydrogen sulfate, which would be H plus 1 SO4 minus 2, cross and reduce, you end up with H2SO4. So if I'm going to get the theoretical percent composition of the entire compound, I have to get the percent composition of all of its elements. That means I need to get the percent comp of hydrogen, the percent comp of sulfur, and the percent comp of oxygen. So what we're going to try to do is utilize our equation here and then plug some numbers from the periodic table in, because it is a theoretical percent comp, to get us a answer for the percentage breakdown of each of the elements. So if I'm going to try to find the percentage of hydrogen, it is going to be equal to the mass of the element, the mass of hydrogen, divided by the mass of the entire thing, H2SO4, times 100. Now, be careful. The number I get off the table is not H2, it's just H. So whenever I do this with numbers and I go to plug in, I am going to take 2 times hydrogen off the table, and then to get the bottom, I'm going to have to take this compound and break it down. 2 times H plus 1 times S plus 4 times O. So, if you look at the periodic table, we need 2 times the mass of hydrogen for the top. And if we look at hydrogen, remember, hydrogen is the only element that we go 3 places past the decimal, which makes hydrogen have a mass of 1.008 grams. Now, for the bottom, we're going to plug in the mass of H2SO4, but I'm not going to try to jam all that math in there. I'll do some legwork down here, and then we will plug it. So here we're going to take 2 times 1.008 plus 1 times sulfur, which is 32.07, plus 4 times oxygen, which rounds to 16.00. And if you get out of calc and do that, I'm fairly certain it's 98.08, but let's double check. So 2 times 1.008 plus 32.07 plus 4 times 16, and we get 98.09, so I'm glad we checked. Right, so this mass here is 98.09 grams. And then times our 100%. The good news is you'll only have to do this bottom part once, because for sulfur and oxygen, the mass of the compound is going to be the same. It hasn't changed. It's still H2SO4. So if we do the math on this, we'll take 2 times the 1.008 divided by 98.09 times 100, and we will get 4 sig figs in this number. And with 4 sig figs, it looks like we get 2.055% hydrogen. So we're going to try to do the same thing for the sulfur. And so I'm going to erase this little bit of scratch work here to give us some space. And the only difference between the equation that we just used and the new equation is going to be, instead of the mass of hydrogen on the top, we're going to have the mass of sulfur on the top. Right? Now when we go to plug in, because it's H2SO4, there's only one S, I don't need to multiply anything. So I'm going to take 32.07 grams over the mass of H2SO4, which we still have from up here, so I'll leave it in red, for the H2SO4. So, watch your sig figs. Again, you'll get 4, 32.07 divided by 98.09 times 100. And I get 32.69% for the salt. Now, we could do the same exact thing for oxygen, where we take the mass of O over the mass of H2SO4, and it would be 4 times O, which would be 4 times 16.00 over 98.09, and get yourself that number. You can also try to shorten up the amount of legwork you'll have to do because this compound is made up of 3 different elements. If I know the percent of 2 of those 3, I know the percent of the third one because we know they have to add up to 100%. So I could simply, instead of repeating what I've done here, take 100.000%, and I always make my 100 match how many ever pass, the most goes, minus how much of it's hydrogen, 2.055%, minus the sulfur, 32.69%. And we know that whatever's left has to be of the oxygen. So sig fig rules change here. Places past the decimal, 3 here, 3 here, 2 here, means I can only go 2 places past the decimal with my answer. So 100.000 minus 2.055 minus 32.69 gets me a value of 65.26% oxygen. And due to sig figs, these may not always add up perfectly to 100, but you will get yourself an accurate answer by using 100 minus those. If you prefer to do the mass of O over this, that's by all means going to be 100% correct. I will never take points off for solving a problem correctly just using an alternate method. So that's how we tackle a theoretical percent composition problem. Notice we use the periodic table and we have to multiply by the number based on the formula that is there. Let's take a look at how we do an experimental percent compound. This one here is number 2 on your handout, but it says, what is the percent composition of a 37.47 gram compound of barium oxide that is determined to be 4.73 grams of oxygen? The way I know this is an experimental or actual percent composition problem is there's numbers given to me. In the last one, all I had was a formula. All right, so with there's numbers being given, that means we have to be doing some actual, and we have lab data and the numbers are given. The good news is we still use the same equation. If I want the percent composition of barium oxide, obviously the 2 elements involved are barium and oxygen. So I have to get the percentage of barium and the percentage of oxygen. Our equation stays the same. We use the mass of the element over the mass of the compound. So if I want the percentage of barium, I need the mass of barium over the mass of barium oxide times 100. Now, some people say, well, how do we do this if we don't have a formula? Very simple. If you don't have a formula, somewhere they have to tell you what the mass of the compound is. Whether they call it an unknown compound of barium and oxygen or an unknown oxide of barium, it all means that you can't use your knowledge of what the formula should be to get what this number is. We cannot use the periodic table. And sure enough, if you look, they tell us 3747 is the mass of the barium oxide. Mass of the barium would also have to be given, and if you take a look, it's not given right here. Right? So we have oxygen, so that sets us up to do the percent oxygen problem. So we would need the mass of oxygen over the mass of barium oxide times 100. That we have all the information that we would need. They tell us that the oxygen mass is 4.73 grams divided by the barium oxide, which is 37.47 grams, times 100. And you'll see that you get 4.73 divided by 37.47 times 100. We only get 3 sig figs, so my calc says 12.62. So that means this is 12.6% oxygen. Now, for the problem above, I could just take 100% minus the 12.6 and get myself an answer. But I'd like to show you something different. Say, for instance, you have the barium oxide but not the barium. I'd like you to see how there's a different way to get the mass of barium. Right? And most of you have probably figured this out by looking. Right? But if I need the mass of just the barium, it's going to have to be the entire compound, which has barium and oxygen. Taking away the oxygen would leave me just the barium. So if I take the compound minus the oxygen, that's going to give me the mass of just the barium. So if I take my 37.47 grams minus my 4.73 grams, what's left has to be the mass of the barium. So that's a different way of getting the mass of the element if it's not directly given to you. So if we take 37.47 minus 4.73, looks like we get 32.74 grams of the barium. Now I can plug in because I have all the numbers I need. 32.74 grams of the barium divided by the 37.47 grams of the barium oxide times 100. And we plug that in our calc. And I get a value of 87.38% barium. Right? And notice, if you did this with the 100 minus, it would tell you that you're going to get a value of 87.4, and we're at 87.38, so we know that doing the alternate mass method is okay. Right? So that's how you do an actual problem. Notice, at no point did I slide my periodic table board in and use the periodic table. All of the numbers that I have were either given to me or I subtracted 2 and used the process of elimination to get the third. The last thing we can do is use the percent composition idea to determine how effective we are in the lab. We did an experiment where these are the numbers that we got. And what will happen is we know that that compound should have a certain percent by mass. So a problem like that would look like this. For the previous problem, determine the theoretical composition of each element in barium oxide, and then determine the percent error for each. I'll figure out what the amount of barium should have been, and then compare it to my percentage and see how close that we were. So let's go ahead and do that. If I'm going to solve this problem, it is asking me first to get the theoretical composition. Right? And remember, the theoretical tells me that I need to use the periodic table. Now you can use what you know the formula of barium oxide to be, which is BaO. So that means we need to find the theoretical percentage of barium and the theoretical percentage of oxygen. Okay, this should be old hat, so to speak, at this point. Third time we're doing this. I think the percentage of barium is going to be the mass of Ba over the mass of the whole thing. BaO, mass of element over the mass of the compound, times 100. And the oxygen will be the mass of O over the mass of BaO times 100. So we'll go up to the periodic table and we'll get the numbers that we need. Right, mass of barium is right here. It's 137.33. So I plug that in on top. Notice nothing multiplied there because BA has no subscript. Mass of BaO is going to be the 137.33 plus oxygen. So 137.33 plus 16.00 is 153.33. Times 100, and we'll get ourselves a number. 137.33 divided by 153.33 times 100 tells me that this compound with 5 sig figs is 89.565% barium. Doing the same thing for the bottom portion. Mass of oxygen is 16.00 grams divided by the mass of the whole thing, which is still 153.33 grams, times 100. I'll find out that the compound is 10.44% oxygen. And notice one less sig fig here because the 16.00 has 4. It limits me to 4 sig figs in my answer. So to finish out this problem, the question wants to know, well, what was my percent error? I should have determined that it was 89% barium and 10% oxygen. What I actually found when I did it was that it was 87% barium and 12% oxygen. So obviously there was some error in my experimental values. So how we do a percent error problem is the same way we've done percent error from the beginning of the year. Right? Finishing out, percent error is equal to A minus E over A times 100, where A is the actual or the theoretical, right, and E is the experimental, right, or A is the accepted rather, right, minus the experimental. Well, we have both of those values. Right? The board I'm looking at here, right, is the actual values, right, which is our E, right, the experimental, because we did an experiment to get those. So if I'm going to do percent error for barium, and then percent error for the oxygen, what I'm going to do is take A minus E over A times 100 for each. So, for the percentage of barium, the experimental and the actual are right here. All right, so the theoretical we calculated is 89.565%. That is the accepted. Minus the experimental, which was 87.38%, over the accepted, which was our theoretical, 89.565%, times 100. So solving that problem, always do the math in the numerator first, 89.565 minus 87.38. Right? And when we do that, this goes 3 past, this goes 2 past. I can only go 2 past. That makes that be a value of 2.18. Right? And then we take the 2.18 divided by 89.565 times 100. And we get 3 sig figs. So we have a 2.43% error. Doing the same thing for the oxygen, I would need the accepted minus the experimental divided by the accepted times 100. So the accepted value of the oxygen was 10.44%. Minus the experimental, 12.6%, divided by the accepted, 10.44%. Again, do the numerator first, 10.44 minus 12.6. We only get to go one place past the decimal, so that ends up being negative 2.2. And then negative 2.2 divided by 10.44 times 100. That gets me a value of 21.07. With two sig figs, we have to call that 21%. And remember, the percent error problems are really just absolute values. Negative or positive, it doesn't really matter. It's how far from the zero value you are. Right, so we had a 21% error in our oxygen, and we had a 2.43% error in our barium. Right, so that's how you can couple a theoretical percent composition problem to what we've done in the lab to measure how we were doing in terms of our effectiveness. I hope this helped out if you were having confusion on percent composition. As always, if you're still having trouble, feel free to come in for some help.